as a system has three major functions: positioning, navigation, and timing. Dr. Han Chunhao is an expert of the timing of the GNSS system, especially the basic system. And today is a very special day. It's a Teacher's Day in China. So let's say thank you for Dr. Han to come to give us a lecture.
Thank you.
And now we can start.
Okay. Let's begin. Ladies and gentlemen, it's my pleasure to attend this workshop and to discuss the space-time reference of Beidou system, and just like I introduced by Dr. Cao. My name is Chunhao Han. I work in the Beijing Satellite Navigation Center before retired. You know, the Beijing Satellite Navigation Center is the operator of Beidou system. And today, I wanted to discuss the main contents, the brief introduction of BDS, the principle of satellite navigation, BDS time transfer, and the concepts of relative reference systems, and the space-time reference of Beidou satellite navigation system. And at the end, give some summary. Do you speak Chinese? Little? Yeah. Do you know the Chinese meaning of Beidou? Okay. Most know. Maybe someone do. Okay. And Beidou, Bei, the Chinese meaning Bei, pronounced Bei. Bei means north. And the Dou, like this. Yeah, it's a Chinese pack. It's a measure device for in ancient China, Dou. So at a clear night, if you look upon the north sky, you will find 7 bright stars. The Big Dipper. Yeah. So in Chinese, Beidou means this 7 stars, 7 bright stars. Big Dipper. So you know, if you lose your way in night, you may find the 7 stars clearly, and you will find the way you go home. So to give you a direction on navigation. So the Chinese satellite navigation system is named Beidou. You also know Beidou, the shape of Beidou, like a spoon. It's also, you know, the ancient Chinese equipment compass. So in earlier, the Beidou satellite navigation system is also named compass. Or come from the Big Dipper. Okay. the Beidou. Do you understand? All we know, since July 31st, 2020, Beidou 3 navigation satellite system has been officially operational. As a major national infrastructure, BD3 provides global positioning, navigation, and timing. This is is also named PNT. You know, the basic and open services. Yeah, and also we have global short message communication and the search and the rescue service. At the same time, it also provides that satellite-based augmentation service. Price point positioning, PPP, resident short message communication, and other services in and around China. But maybe just have a little test you will ask, what PNT? It's a term from USA. You can find the answer from the website of US communication. So let's have a review. And the PNT is a combination of 3 distinct constituent capabilities. And positioning is the ability to accurately and precisely determine one's location and orientation 2-dimensionally or 3-dimensionally when required. This is must reference to a standard geodetic system. Must have a geodetic reference system, and such as World Geodetic System or WGS 84. This is for GPS. Navigation. Navigation is the ability to determine current and desired position relative or absolute, and apply corrections to course, orientation, and speed to attain a desired position anywhere around the world, from subsurface to surface, and from surface to space. And timing. Timing is the ability to acquire and maintain accurate and precise time from a standard coordinated universal time. You know UTC? Do you know UTC? Yes. Oh. It's the civil standard of time. You know Beijing time, or maybe you know the standard time of your country. It's or the standard time, national standard time from UTC. For example, Beijing time is UTC and 8 hours. That's right. And Tokyo time is and 9 hours. something just like so. And we acquire and maintain service at the standard time anywhere in the world and within user-defined timelines parameter. At this time, you can maybe you can tell me the UTC time, the standard. Also, timing also includes the time transfer from one point to another point. But in Chinese, this translation, the Chinese translation is wrong. You know, PNT in Chinese, what in Chinese? No, Chinese 定位、导航、授时、授时 means time service. Time service or time dissemination in English. Time service and time dissemination is the Chinese meaning 授时. So I just want to say it's not correct. It's things in Chinese. You should acquire, attain and maintain it. We see this timing and the user position, not the system. I'll just that. And you know, Beidou system have just like GPS, 3 segments. You know, 3 segments. And we know the space segment is a constitution of satellites. We have now 3 kind of satellite geostationary orbit satellite and inclined geosynchronization orbit. Inclined, the equator. And the middle Earth orbit, MEO. From this, you know the Chinese satellite navigation is different other systems. It's different to GPS and GLONASS and Galileo. Different satellite constitution or different space segments. Here I show you the 7 major axes and eccentricity, inclination, and this number. And for normal performance of a satellite system, you should have a control segment. The control segment in Beidou consists of master control station, uplink station or uploading station, and monitor stations. the master control station window in Peking, and the uplink station we have other two upload stations in Xinjiang. Do you know the province of? Do you know the Urumqi? Yeah, it's a Kash near Urumqi. A Kash is an upload station, and another one in the South China, the Hainan, the province, the island, the South Island of China, uh, in the south of the south of China, Sanya, the Hainan province. Yeah, yeah. The two up, but Peking, also a master station is also a lot uploading station, uplink. And the modern station main distributed around China and also several monitor stations abroad, out of the China, yeah, overseas. So you also know the third segment is the user segment, the equipment of the receiver or the receiver of the user. Yeah. And here the brief introduction. And also, you know, I think it's very important for us to understand the satellite navigation system principle of satellite navigation. So we know for any user, you have a receiver to receive the space signal navigation space signal from satellite navigation satellites. Okay, we know all the space segment satellites emit space signals to the ground. Okay, so here show you the propagation equation of navigation signal. This is the position of the satellite, and here the user, and v is the velocity of the light or the signals. You can write this equation. And the space signal emit at the time E, and it's be received at TR. So you can get from the satellite position to the user's coordinates, the position coordinates. And you may know the light velocity or the light speed is changed, not a constant. It's changed by the troposphere, the ionosphere, and gravitation field. This is the effects of relativity. And also this is caused by the atmosphere, the ionosphere. So you can get time delay of propagation like this. Here I just mentioned the transmitting and the receiving the time and the coordinates of the base centers for satellite and for the user receiver, the antenna base center. From this equipment, we can get the pseudo range. The pseudo range means here, the pseudo, if here show you if the user user and the user receiver have a clock. Yes, and we also know satellite have a clock. The readings of satellite clock at the emitting time means this one, and the user clock, the reading of a user clock at the time receiver received the the signal arrived at the user. So these two time readings from these two reading times we can get the pseudo range. Pseudo range. Here show you. So if we get the pseudo range, we can get the distance from the satellite to the user, but it includes the difference of clock. So from this we can know a global navigation system is essentially a precise time measurement system. Yes, it's a time measurement. All these parameters is a time parameter. All this time delay, the transformation time. So a satellite system, navigation system is a time time synchronization and time measurement system. If we know the satellite coordinates and the clock difference or the bias of the clock and the propagation time delay, signal time delay, also maybe the other related parameters, the troposphere time delay and the gravitation time delay, we can get the determined parameters, the three dimension space point, the user, and the offside or the pairs of the user clock. 4 parameters, 3 dimension position, 3 parameters, and plus 1 time offside your clock. Your clock is not usually is not correct. So 4 parameters, we should get 4 observables. Yeah. If you observe 4 navigation satellites 4 navigation satellites, you will get 4 pseudo range observable. So you can solve this equation to get the undetermined parameters. This means that the user prediction and the user clock offset. This is the principle of satellite navigation center. You should know, and it's very important to know that if you want to determine your prediction and your clock offset, you must observe more than 4 navigation satellites. This is the first. And you also know if you want to do this, you must know the prediction of satellites. And you also know the clock offset of satellite. All these parameters you should be given. You should given it. Given. It should be given. Okay? All these parameters you should know. If it's an annual parameter, we cannot do prediction. So most of the workers is done by the master control station. The master control station to first you should to determine the satellite orbits. Sorry. To determine the satellite orbit, to give the prediction to user the orbit parameters or the orbit predictions, the satellite predictions. You also should know the satellite clock bias, the offset. So you should do some time synchronization or the satellites. And we also to determine the transfer time delay. I mean it means the signal from the satellite to the Earth, the time delay from satellite to Earth, because the media, the atmosphere, the gravitational field, and so on. The ionosphere. It changed the signal propagation speed, the velocity. We should do this by the control segment, the master control station. And how to do this? We should do this based on ground observations. So we should distribute different monitor stations at different positions. So the monitor stations provide the observables used by the master control station. And after we determine all the parameters, we also should upload to the satellite. You know, based on satellite system, we uploading all satellite parameters by 2 hours. 2 hours, we update the satellite navigation parameters. Here, I just mentioned here the Beidou satellite navigation system have many differences from other GNSS. One is the space segment, different orbits, and also we have very important difference between this GNS. The Beidou satellite navigation system uses two-way time and frequency time transfer from the GNSS satellites to the ground master station. Why? Just now, we consider that the limited deployment range or the area of a monitor station. If you want to accurately determine the satellite orbits, the best way is you deploy the monitor station all around the Earth. You can track the satellite at any time. But the China area is limited. So most of the time, we cannot observe satellites. This is one reason. And we also know at the beginning, the satellite clock is not an ideal clock. It's the stability. It's performance not very well, not very good. It's about 3 minus 13, about 1 day, about 30 nanoseconds at the beginning of the Beidou satellite navigation, Beidou 2. The area segment. No. I mean, in Beidou satellite navigation, the regional system is a performance of the normal performance and 2012 the system. The consists of five GO and 4 IGSO and 4 MU satellite. The consistent the constitution of the base segment. So because these two reasons, we choose two-way time and frequency transfer. It's used between the satellite and the ground station, uploading station, including the master control station and time security uploading station. With two-way, we send that signal to the satellite, and the satellite send a signal back to the station. So we can know the time difference between two clocks. It's very accurate in 1 nanosecond level. 1 nanosecond level. We can accurately get the offset between the ground station clock and the satellite clock in 1 nanosecond level. You know, 1 nanosecond means about the space time. Do you know? Do you know 1 nanosecond equal or the light propagation the distance? You know, it's about 30 centimeters. Yeah, 1 nanosecond. In 1 nanosecond, almost it means about 30. What, for example, is one if the time offside have a 1 nanosecond error, you mean that the distance between the satellite is going to have about 30 centimeters error. Okay, 1 nanosecond. So I just mentioned BDS is essentially a system of precise time measurement and time synchronization, and a larger scale space near the Earth. This is very different from other GNSS systems. At present, the daily frequency stability of the BDS satellite atomic clock has reached the level of -50. It's almost 0.1 nanoseconds a day, or the difference of the 15 is means a whole day the satellite error less than 1 nanosecond. Less than 1 nanosecond. This means the distance from the satellite to the Earth is very correct. The error caused by the clock is less than 30 centimeters. Or satellite clock is very accurate, very stable at present day. But at the beginning, that's only minus 13. Minus 13. 100 times. Almost 100 times. At this precision or accuracy, which now the time synchronization accuracy is required to reach 1 nanosecond or even higher at the present, and the accuracy of space-time measurement and observation model, is required to reach the order of a picosecond. Picosecond. 1 nanosecond equal to 1,000 picotimes. Picosecond. It's about minus 12. You know, 1 second equal to uh, 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 100 millions millisecond. And 1 millisecond is about 1,000 nanoseconds. This means you know, the transformation velocity of the speed is about 30,000 300,000 kilometers meters 1 second. So a millisecond is about 300 meters, and 1 nanosecond is 30 centimeters, and 1 picosecond, you know, is less microsecond. No. Macrosecond is 1 second equal equal 1,000 millisecond, and 1 millisecond equal 1,000 microsecond. The 1 microsecond equal 1,000 nanosecond, and 1 nanosecond equal 1,000 picosecond. Okay. So at this level of accuracy, the theory of modeling should be established in the theory of relativity. Or the relativity is a theoretical basis of precise object determination, time synchronization, and measurement modeling of BDS. The theory base is relativity of BDS. You know? So if you consider the principle of satellite navigation, you should review the space-time theory. Space-time. I just mentioned different. So we have learned different space-time theories. Just we have reviewed at this class. You know, any global navigation satellite system is a radio navigation system or a project time measurement system. The theory of general relativity is the base of precise measurements in large scale of space-time. As given by Einstein, you know, Einstein. So, but most of us know relativity, but I don't know, think so. I would want to understand relativity. How to understand the difference between the general relativity and the Newtonian mechanics? Most of us familiar with Newtonian mechanics. So here I just have a reviewed of the theories of space-time. we learn from the primary school, maybe a high school. We will, or I think all of you learn about the geometry. Geometry. But do you know the basement of the geometry? Euclid geometry? Do you know? I think Euclid is one of the most of us think is one of the most one of the most scientists of ancient. To my opinion, it's the first. Maybe I think it's the number one. It's the most great scientist. It gave us a book of elements before 2000 years ago. Euclid. And is one of the first to us to use rigorous mathematics proof and to do poor mathematics. I don't know, it's a poor mathematics. Euclid think it's the elements. It's the elements of our universe. It's most of the scientists think geometry is not mathematics, it's physics. Yeah, you think it's mathematics or physics, but I think it's physics. Why? Do you know that I just asked you? Do you know the basement of Euclid? Euclid gave 5 axioms. What axioms? You know axioms? Axioms is absolute act, not should be, not needed to give proof. It's accurate, just like, you know, things which are equal to the same thing are equal to each other. And if 5 are basically given by Euclid, and the whole is greater than the part, that's absolutely correct. But can you prove it? Can you prove? It's a fact, absolutely. But you can't prove it. This axiom, 5, the basement is the 5 axioms, Euclid. And also we know Euclid gave 5 postulates. What postulate? Postulate is also correct, but not absolute. It may be wrong. It may be wrong in some cases. So Euclid is so great. They tell us, he tell us, a straight line segment can be drawn, join any 2 points. Any 2 points can draw a straight line. Euclid think it's correct, but not absolute. And we know all 5 postulates is relative is no this related to the straight line. Hmm? And then to the second postulate that any straight line segment can be extended indefinitely in a straight line. And also three any straight line make a third circle. And also we know the final postulate is the parallel postulate. Up to now, we think many scientists think the 5 postulate maybe not correct. Maybe no parallel. So we have a non-Euclid geometry. That's Riemann geometry. A curved space. You know, the two parallel line and around our Earth cannot satisfy this postulate. But no one to think of strictly. I just want here to ask you a question. What is a straight line? What's a straight line? Can you answer me? No scientist. And we also know your classical mechanics is constructed by Newton. Newton, for the force, the theory is based on Euclid geometry. Based on, and also we know a free motion is a straight line. Free motion is the base. It's a straight line. You know, Newton tells us a free motion of an object is a straight line. Still, I want to wonder what is a straight line? Newton not give us answer. It's based on Euclid geometry. So straight line. Straight line. What a straight line? Maybe suppose we are on the we are taking a flight. You on the all of us on the airplane. If you throw down something, for example, a puzzle down to the earth, could you tell me the orbit of this puzzle? The orbit, yeah, Huang is Huang term. It's a curve. If you stay on the earth of the surface of the earth, you may parabolic. Yeah, curved line. But I just mentioned you are on the airplane. What are you found? Puzzle down to the earth. It's a curved line, a straight line. From your eyes, you can do a test. Yeah, it's a street. Or if you take a bus, take a train, take a plane, or put down something, it's a street. You take the bus, you maybe if a free motion, uniform motion, you can find everything as a aesthetic. It's a point. But maybe uh, you 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 were observe it in the ground. You were what you were saying. It's a your motion. It's a it's motion. It's a line. Yeah. So I just wanted to tell you in Euclid geometry we have a point, a line, a straight line, a curve. All this is not objective. Not a point. You see a point. Maybe other one. To other one, it's a line. Maybe to you a straight line. To another one is the same. It's a curve. So curve, curve line, straight line, point is not objective. It all depend on observer or view. Different observer will have different answer. This what is it? This means relativity. Most things in our universe is not absolute, but relativity. Most of. For another example, let's do a game. Clap your hand. It's happened in our universe. Yes, it's a maybe you can think it's an event. And 1 second later, you do it again. This another event happened in our universe. Yes, 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 yes. I I wanted to ask you what is the time interval you can answer 1 second. Yes, yes. The time interval of these two events is 1 second, but it's not very correct. I just you can say I want to ask you other question. What is the space distance or spatial distance of these two events? Can you answer it? Okay, answer it. These two events. Yeah, distance. Hmm? Spatial distance. You you can answer these two events. Clap. You could just clap your hand one time and
We think it's 1 second, but it's not exactly 1 second because we cannot measure the distance.
can you answer the distance, the basic distance? You can maybe one is the answer is you tell us just zero maybe zero is the basic distance. Yeah, it's right. I don't. I'm not moving. I'm not moving. Just find the basic distance. Okay, not correct. You answer. You another. Yeah. Not you climb your hand, and after 1 second, I climb your. I climb my hand. Other event. Can you tell us the basic distance? You how to measure it? You want to how to measure it? You can't do anything measure. Oh, I just want to tell me how far are you from me? 3 meters. Yeah, 3 meters. And she measured 3 meters. Is that correct? No. Why? Not very correct. I don't want you to say a very correct
Okay,
answer.
okay,
You just
let's suppose
a promise.
let's suppose 3 meters.
Huh?
Let's suppose 3 meters.
Oh, or maybe 3 or 4. Yeah, that is one. But you know the Earth is rotating, and 1 second, the linear velocity about 450 meters 1 second. So you put these two events, the time segment, the time interval is 1 nanosecond, the 1 second. So 1 second, the Earth rotates 400 meters. Yes, so you can answer these two events. The distance is changed. Yeah, you want answer for you. You will give you can tell us the distance between um, Muhammad and me is about 3 or 4 meters. But otherwise, if you stay not on the Earth but outer space, you will answer me 400 meters. Is it correct? No. You also know the Earth is the orbital of the motion, annual motion, annual motion around the sun. Around the sun. The Earth is moving around the sun. So the 1 second, the velocity, orbital motion of the Earth is about 30 kilometers. 30 kilometers 1 second. So you can maybe another answer. 30 meters far. These two events is 30 meters far. 30 kilometers away. So we can get many answers. Different observer with different. You know what time segregation? If I see you do something at the same time, for me, I see you do something at the same time. If you are if between us, I mean the distance is equal for for Edward and Muhammad is far from me. They have the same distance from me. If I see you do something at the same time, I think you are time synchronization. At yes, you do the thing at the same time. Yes, you just do the thing at the same time because I say they do the thing at the same time and the distance is equal. This is the same time. The definition of same time is also given by Einstein. Einstein time synchronization. This is named Einstein time synchronization. So I think I just mentioned distance depend on the observer or the reference system. So time synchronization is also dependent on observer. So I hope from today you will have the conception of dialectic. Oh, take a short rest. 10 minutes.
Guys, this morning task we got 3 excellent answers, 3 excellent trainings. Bali, Hoza, and Huang Zhixian. Okay? Congratulations. And now comes the penalty. I'm serious. Fahad Bakar, you got 10 push-up.
10 push-ups. I cannot do seriously.
And Hira Hilbert, 10 push-up. You got 2 wrong answers, but you got the bonus, so minus 10. 10 push-up. Benjamin Colley, it's very pity, 30 push-up. Anatoly, you got 20 push-up. Sorry. Okay. And Kong Zhuoyue, you got 20 push-up. Yuan Huirong, 20 push-up. And for Shi Zhongyu, 40 push-up. But for the ladies, you can choose to sing a song. Okay? If you cannot do push-up. So, gentlemen, come. No, don't be shy. Gentlemen, please.
Push-up is much difficult than singing.
Up to you. Okay? All up to you. Okay? So, gentlemen first. They're doing it right now. Then we have break. And ladies, try to think what you're gonna do. Fine, fine. This is a push-up. Come on. Come on. Don't be shy. 20.
No.
This is not a push-up. This is a push-up. Benjamin, come on. Yes, for everybody. Take some videos. Take some videos. Come on, come on. Take some video with yourself.
Okay. 1,
Maybe sing a song.
4,
See?
5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8. Starting.
Okay. So? Yeah. So, you have to do the penalties. Up to you.
Yes.
No push-up, maybe other things. Fine. Come on, Gilbert. No, maybe like this.
I just do like this one.
Yeah.
Okay.
Take some pictures.
3, 4, 5, 6,
照他们录的时候，录一次。
9, 10.
It's fun. But you have to.
No,
Well,
sing,
others.
sing
With
or dance.
education.
Dance.
Yeah.
Yeah, dance. Not sing, dance. Yeah,
Chinese song.
yeah,
Yeah.
Chinese song.
yeah.
Yeah, you can sing with all the girls. 你们可以一起来唱嘛，对吧？
我们都有一
Good,
个
good.
家，在家中国，兄弟姐妹多很多，亲戚也不错。家里放着杨家楼，是长江入黄河呀。爱祖母那么啊，水西看上坡。我们的大中国呀，好大的一个家。天空那个的山，那个风吹和雨打，我们的大中国呀，好大的一个家，永远那个永远那个。唱歌。
I'd like to sing a song for you after the class. But this time, I just when I was young, I listened to the radio. I just do the push up here. You can sing and push up. Can't have push up, so it's easier than push up.
您刚刚讲的这些就是参考系的问题，它就是跟延时有关的是吧？
嗯。
因为它是
参考系跟时间传播有关，对。
参考系跟时间传播，
对
就是为了就是缩小那个时间间隔，对吧？是还是
缩小间隔？
就是延长，就是延短。
不是这个意思，就是说你信号的空间轴取决于两个因素，一个就是说你的不仅参，就是首先来讲，别说参考，这个两个点的相对关系，对吧？
两个点的相对关系。
位置关系，这两个一个卫星和一个用户相对位置关系。第二个来讲，还有你的传播介质。
传播介质。
你的传播速度肯定是有关系。
传播速度跟介质。
对呀。
就是介质是速度取决于介质。
对，然后你在确定点的时候和参考系有关，就是什么叫同时？你肯定是说，我比如说卫星要同时发一个信号到你，什么叫同时？你先要回答我这个问题。
同时就是这边开始，这边也开始。
对，你看我和上海咱们同时发生，北京和上海同时发生一件事儿，什么叫同时发生一件事？你也一起发生。
但是他们需要一个参考系，就是因为他们两个有时间差。
对，不是有时间差，有空间位置差。你有空间，你要在这儿，我们说我们两个没有，我们同时叫 co-moving around the universe， 对吧？我们两个在一起，你可以比较时间。分开以后你怎么比较？就有约定了。距离是和空间有关的，然后距离是和空间点和观测者有关的。你不同的观测者，也就是说不同的，我举个例子吧，比如说火车，假如说这个火车的一个车厢有光控的光明一管来控制了两个门开关门。如果这个灯泡放在这个车厢的正中央的，然后它灯亮了，那么它发信号到车的两边去，两个门嘛，它肯定是同时开门的吧，同时关门吧。那对车上的人永远看到，如果这个车跑去了以后，那对月台上的人来看会是什么结果？
那可能是有延时。
就是你看哪个先开，哪个后开。
就是他在走的时候他开了。这样的话是后边的先开。
对，
就是对他来讲。
对，就这么个观点。你在车里边的人，如果这灯就在中央来看的话，他因 OK。So I hope you have the concept of relativity after today. So let's go on. the first one, I don't think it's the first one. In many scientists at that time of Einstein time, many scientists maybe think that Euclid or Newtonian mechanics is not very correct. So to Einstein, he told us no absolute time and no absolute space. But space time, space and time together as a whole is one is one thing. It's not it's the same. Not we don't think it's one thing. It's correlated. It depends on time. It depends on the space, and the space depends on time. Or we can answer you space time depend on observer, the viewer. Different one for I just mentioned, for example, the two events happened in our universe. I answer you, what is the time interval of these two events? What is the spatial distance between the two events? Different people will give different answer. So I continue to ask you, no objective answer. Time depends on, just because the distance depends on the observer. And so the time also depends on the observer. I ask you, the of nature answer. But you know, the two events happened in our universe is objective. Yeah? The absolute. It's absolute. Two events. You clap your hand. This event happened in your, and you clap your hand. The also event. But the time interval, the distance, the distance depend on observer. Different one give our different answer. No observer. I ask you, if we can find something absolute to this, to express this two, I mean the interval of these two events, you can find something to absolutely express the interval of these two events, because it's natural happening. You can find that the interval is space. Okay, we consider these two events and not in space, not in time, but I wanted you to determine the interval of these two events in a whole space plus time. This is space plus time. The space time interval is not changed for anyone. The space time interval, the space time interval is not changed. This is special relativity and special relativity. And also no straight line. No straight line. We cannot find a straight line on our surface. You cannot draw a straight line any between any two space points because we have gravitation field. Gravitation. So all ground is not a place. It's a surface of a curve. Yeah, it's a curve. All ground surface. It's a sphere. Yeah, not straight. But also is you can imagine the space time. It's not you cannot give us a straight line, a large scale. Basic is to think the gravitational, not the gravitational bit, the gravitational effect, not a force, a geometry. By Einstein, it's a geometry characteristic. The gravitational effect, not a force, is a gravitational effect perfect for the space. So we cannot use Euclid geometry to express or you should use pseudo-Riemann geometry to express the gravitation field and the space. This is general activity. You maybe find it's very difficult to catch the relativity, to understand general. Maybe you who learn this course, general. Anyway, learn general relativity. It's very difficult to learn general. I think many I have thinking almost 30 years. So here you will show you many people don't know general, have no relativity connection and understand how to catch the general relativity, how to understand the effect of relativity. And I write a book named Principle of Space-Time Measurement. It's from Euclid, geometry, Newton mechanics to general. But it's in Chinese. Here I just one. If you read Chinese, maybe much difficult. Yeah, you can read it. I think this. I write this book. I think it's for 30 years. I write it for 5 years. I will give you. You can from the website. Here, I told you any theory is constructed, must based some axiom and some postulate. Any theory, Euclid geometry based on 5 up and 5 up. So here I give you 9 positive. In the second chapter of this book, I give you 9 positive. Show you here. The first postulate is about our universe. Water is our universe. Water inside our universe. The universe is a continuum of time, space, mass, and energy. The four are relatively independent. This means the mass different from energy. The space different from. Everyone can feel. You can feel the space. You can, and also we can feel some. The four are relatively independent, but also unified with each other, and have a certain interaction. Everything between everything have interaction. This is postulate 1 and postulate 2. It's about local flatness and relativity of space. The time and space of an observer, when you see the time and the space, you must point someone or certain observer because it depends on the observer. So anyone or part of anyone our space, our space, three-dimensional space, and also a one-dimensional or anyone. Time and space different for anyone. It's different, but independent. And for any observer in the state of nature motion, in nature motion, freedom motion, nature freedom motion. Are you freedom motion in the universe? No, because the way stand on the earth. But the planet, that's the freedom motion. Yes, a planet is a freedom in nature. It's freedom motion. Yes. That's right. For any freedom motion, if you are freedom motion, your space and your time is present. We know for any observer in a state of nature motion, freedom motion, the time is uniform and the space is free. The place is it's a uniform, and that means Euclidean geometry is correct. So Euclid is correct. In any local space time, Euclid is correct. But the large space, just we know, the plane of water in low pressure is a plate. Yeah. Water surface in local area is a surface. The surface is a plate. But in large scale, the sea or the ocean is not a plate. It's a this is the third postulate is the unity. It's the unity of the space and time is a postulate. I don't I don't know if it's absolute. We know the time independent of the space is also dependent on you. I suppose the postulate we have a unit space, space and time together is a continuous. Is one whole thing. Is the space time. So now there is a unique space time interval between any two events. That is objective and independent about the local space-time of the observer that moves freely is Minkowski space, because you don't have a concept of relativity. What Minkowski space? Minkowski space is three-dimensional real space. You know real space? Or space is real. And one-dimensional imaginary space. Maybe you learn imaginary. 虚数空间，3实数空间 real space real 实数空间 real and 3 imaginary 虚数。三维加一维，this is Minkowski. So I just mentioned maybe certain events between two events. You have a time interval and the spatial distance. And for one, the distance number. And for other ones, and also have a time interval, space distance. Together, the space time distance is not changed, is observed for any. Okay, from this you can get for special relativity. You can get all special. You can give us a Lorentz transformation. Postulate about wave particle duality of light. All substances have the characteristics of emission and absorption of light. Now, light like energy. Light electromagnetic wave. The absorption and the release of light-like energy appears a quantum. Quantum, quantum. 量子特性啊，and it propagate in form of wave， 它传播的时候有波动，in space time。The propagation speed is only related to the propagation medium. Atmosphere, ionosphere, independent to the observer, independent to the soul, the transmitter device, and also independent. This, but it's a postulate, and the postulate by the metric of the base. What? How to measure it? Gentlemen, Mohammed asked me how to measure it. How to measure the space. The standard. The mesh, the benchmark. I mean the benchmark. How to measure space. You should have a standard. Here, I think is a postulate point. The temporal and the spatial measurements in any area of the universe are based on the local light-like energy at the base. It's a standard local light. The speed of light in the vacuum is a constant. And then no, it's not changed. The speed of light is not changed. The time unit of the observer is defined by the intrinsic or proper frequency of some light energy or light-like energy. The frequency. And the length unit defined by the intrinsic wavelength of space. Because you send the quantum emission, the emission, the electric magnetic wave have a frequency, also have a wavelength. The wavelength is to be used and as a ruler to measure the distance, and the frequency is used to determine the time unit. You know, at present, the international standard given by BIPI, Bureau of International Organization, you know, BIPI, you can find in the website, or you know, or the unit is given by this internet, or that is the metrology Bureau of American metrology. We know in our universe we have 7 base units. 7 base units. The first 2 is the second SI second international second unit second, and the SI meter. This is it's a very important thing, you know. The base unit, the definition of base unit is changed from 2018 by the international organization about metrology. You know metrology? BIP. PIPM is the international metrology organization. It's located in France. Just like the United Nations. It's the aim of the meteorology. We hope all universities use the same unit for time society. We have the meter, second meter, meeting. I want to say here, at the present, the ISI second satisfied this question. Postulate fixed. Maybe I want what you learn Newtonian mechanics, you know what the inertia, what is it inertia practice for. It's a very important concept in Newtonian mechanics. Yeah. Oh, here just wanted what inertia, what gravitational field. I think mass and energy form a gravity repulsion field in space-time. In the limited range of an accelerated celestial body or celestial system, because here we know the energy and the mass, who is more important? Mass. So the space-time repulsion field can be represented by inertia and plus gravitational field. What gravitation is the effect of near field caused by the near objective substance. Okay, you know, we just stay on the Earth because the Earth have a gravitation. Yeah, it has gravitation force. We can then near objective generate and the far distance effect. The far distance substance generate the effect to us or is inertia. But you can find what the definition of inertia in your classical mechanics. Here, I think is that near field effect far, because of the far distance, the effect of the far distance mass and energy for all of us the same. We have the same effect. Yes, we have because the local we have the same effect. This is the same effect. Common effect is defined inertia. It's an inertia. It's the same for all of us. So the postulate 7 here I show you is the realize that the gravitational field can be expressed by the geometry of a singular Riemann space named as the Riemann and space, which is the space-time including the inertial and the gravitational field. It's different, so the space symmetry is different from Minkowski. We have a efficient coefficient, like this, like this. This is A, and all these coefficients satisfy the Einstein equation. If you have interest, you may read the general relativity. But I just here give you here. This is all the positive rate, and the positive rate, and 8 what the free motion, or in the absence of external force, not as I mean the freedom, or object moved in space time along short range or geodetic, geodetic, geodetic is the short. The short range is I mean the light of propagation, the propagation of light. It was short, the deep geodetic is the short range, the short range. The path of electromagnetic wave is an R or like geodetic, and the that of mass current is a time like geodetic. Is how to from the geometry, from the geometry of or space time to get the orbital motion of propagation light. For example, propagation light, the planet motion orbit, the satellite orbit, you can get from the theory of general. And also we give the postulate that line. You may ask me in general relativity, Euclid, geometry, and Newtonian mechanics as theory used. I wanted it can be still used. It still have some physical meaning. The observed space that is deducted the effect of gravitational field is a three-dimensional Euclid. And we named it Euclid Newtonian space, in which partition inertial geodetic coordinate system can be constructed in the meaning of Euclidean geometry and the Newtonian mechanics. They are almost the same. And the uniform time reference also can be constructed. In analog space, you can use Euclid. Okay? This 9 postulates. If you are agree that, you can easily to understand what in general relativity, what is time inflation, what is the time is curve. You must have this 9. Okay. Here I'll continue to what time. Oh, quickly. What the Newtonian time is with reference? Or maybe we know. I think we all over the formula this concept. Yeah. Under the framework of Newtonian mechanics, a space reference can be simply understood in a three-dimensional space-time frame. Just like this is three. Here, three dimensional. Okay. activated. And we also should have a clock. We should also have a clock. Our clock is a time reference. Yeah. If the clock is very correct, it's the ideal. So you can give a time. What anything happen in your universe, you can give three-dimensional coordinates. You also give a time reference or what in fact it may be anything happened at what time you can tell. Yeah. If you have a three-dimensional brain and take a clock by your hand, you can determine where the things happen. Three-dimensional coordinates, and you can tell us at what time the things happen. Yeah. This is it's easily done, but in general relativity, it's more difficult. I think I hope maybe it's very difficult to understand. But we know the very important concept is a local inertial frequency. What is a inertial frequency? Just like if the coordinate origin is a mad point, it's freely in our universe. Or I just mentioned the Earth center, the planet, any planet, or Earth is freely moving in our universe. The sun, the Mars, or the planet, the star is freely moving in our universe. So you can choose mass center as the base origin, and you can imagine you stay at the origin, and you have a idea clock, a uniform clock. You may feel inertial reference. And we should ask them the space axis of the coordinate base vector don't rotate relative to inertial space, not rotate relative to the far distant object of you know. We just mentioned the Earth is rotation, have rotation relative to what? Respect to it have rotate. The inertial space. The inertial space you can imagine. The inertial space, we can find the far away distant the far distant objects is not rotate. This is the inertial. At present, we have three very important reference systems. The first one is the barycentric celestial reference system, BCRS. BCRS means that the origin is the is the center of mass of all the solar system. The origin, and which take into account all the dissipation of mass of the sun and the planets. You can imagine you stay at the center of the Earth solar system. you have an ideal clock to take there. It's a BCRS. And all the planet's motion, the orbital motion of our planets is referenced by BCRS. The other important coordinate system is the geocentric celestial reference. The geocentric celestial reference system, it means the coordinate origin is the mass center of our Earth. The Earth center. You imagine you stay at the origin of our Earth. And you have an ideal clock, atomic clock. You stay imagine you stay in the center of our Earth and not rotate relative to far distant objects. It's an inertial reference system. Or we determine all the satellite orbital motion in this reference system, GCRS. Satellite motion around the Earth is referent in the motion as a circle. You must stay at the center of the Earth center. You can see the Earth rotation is Newtonian is about almost the circle. The third, okay, and we also should another celestial reference system is the geocentric terrestrial reference system. The terrestrial reference system, okay, I here show you. The tire is rotated with us or station at any point of the Earth's surface is not changed. This also is very important. And we also know different reference system have different time reference. We know we have for the geocentric coordinate time. Here's the coordinate of geocentric is the coordinate time of GCR, geocentric reference. Then also we know we have a terrestrial time. Terrestrial time TT is a realization realized by TII time interval of atomic internal atomic time TII, and TT is another coordinate time reference of GCRS, geocentric celestial reference system, to express the motion of our satellite. Okay, it's another, it's just the different by the scale. It's not just different by scale. That's the case. It's a concept of relativity. It's a time reference. And I show you another reference time is just mentioned is a terrestrial reference. It's used for to express our station coordinates or station monitor stations. The coordinate monitor is used in GTRS. Okay, I just mentioned it here. Okay, time. In the space-time reference of DDS, I just give an introduction briefly. I think. Okay. two reference systems are involved in DTR. I just mentioned three very important reference systems: GCRS, GCRS, and GTRS. GCRS used for process object determination and time is GTRS. GTRS used for locating the position of the user. We give the three-dimensional user coordinates in GTRS. It's not change for static object on the surface of our Earth. It's not a change. The realize of GTRS is named Beidou coordinate system. Beidou coordinate system is a realization of GTRS. So, the definition is consists with ITRS, International Telephone Reference. Used in IERS. Do you know IERS? International Earth Rotation and Reference Systems Service. And also an international organization to serve Earth rotation and reference systems. Here show you the how to get the three-dimensional space coordinate to get the geodetic coordinates, the longitude and the latitude. The parameters used here in Beidou system. This table 1 show you the reference ellipsoid of Beidou coordinate system. Here show you. And I just mentioned it consists with international telephone reference. The difference between these two reference systems. Oh, okay. Wait. The Beidou space, after Beidou space coordinated space time, we want to know the Beidou time reference. Beidou time reference is different from UTC. It does not have leap second. No insertion of leap second. It's a continuous time scale. It's a continuous time. No leap second in Beidou. So it's not a standard time. It's a system only used in the Beidou navigation. It's not a standard because it have no leap second. So in RISS, Beidou time is counted in week number and the second of week. This is similar to GPS, but The zero point, if the 0 point is chosen at January 1st, 2006, this day is a Sunday. Okay? It's very easy to remember. The Beidou time point, the start point, you from this day, at this time, you count the week number and the second week. Okay? And the maximum week number is this is about 20. Oh, yeah, it's about 8 times longer than the GPS, that of GPS. About 150 years. The period of the week. Okay, this is. And also in RDI that the BDT is counted in year number, and the minute. This is so the January 2006. And at this moment, week number and the SOW are equal to them at this. And the Y number was 6, and the minute of a year is about 48. This is the definition. That is the number. Starting of the, okay. Here show you. You may ask me how to get the standard time from Beidou time. You know. We know conceptually BDT is an implementation, a realization of a telescope. And the telescope time from PI is the realization. PI is the realization of a telescope. And we can from this you can get from TI to BDT, and otherwise you can get from get TI from BDT. And the difference between BDT and UTC is less than 2 minus 14. It's about 2 nanoseconds 1 day. Very, very small. The absolute value of time deviation not exceed 50 nanoseconds. If you get time from a Beidou navigation system to translate your any national time, it's not the error is not bigger than 50 nanoseconds. It's very accurate for most for any user. Your accuracy is not need more than microsecond for any user. So you can get the time. You can get a correct, a very accurate time standard time from Beidou. This is the time detection. Okay, here I show you the stability of the Beidou time. No, you can. It's about 5 minus 15. About this means 1 day less than 0.5 nanoseconds. 1 day. So here I show you some summary. We do adopt a completely different technique. We of time synchronization from GPS, Granada, and Galileo. 2 week time and better for you. You must remember it's very different. Other and second, BDS is essentially a process time measurement and time synchronization system for a large scale space near the Earth. We get the orbit, we get the time orbit, time travel. And the third, general relativity is a basic theoretical framework of data processing in PDI. And four, the observation model of time synchronization and the process orbit determination is established within GC framework in geocentric reference system. And the spatial reference of BDIS is the BDCS. It's a realization of GTM. The BDIS ground station coordinates are consistent with the ITRF 2014 on the level of city. The time reference of BDT is a realization of TT. BDT is a composite of clock, composite clock maintained by the master control station. And the frequency deviation of BDT is less than 1 minus 14. That's about 2 nanoseconds one day. Okay? And the time offside is less than 50 nanoseconds relative to EL or UTC. The coordinate transformation between BDCS and the GCR is consistent with IE. Okay. So if you want to know more details, you can refer to this article. With reference available now decentralized. It's published at Satellite Navigation. Thank you. Do you have any question? Okay.
Okay, thanks for Dr. Han's lecture presentation. If you don't have any question, we are here today. Okay, thank you, and enjoy your weekend. See you next Monday. Thank you.
Very good. If you have any question, you can ask. Right? Later, you can maybe you